Welcome everyone to my talk. My name is Wombo. Today I'll presenting FAIR. This is a joint work with my collaborators and advisor from Penn State and UIUC. With the great success of deep learning technique in other application fields, in recent research, these techniques have also been applied to security applications, such as malware analysis, intrusion detection, and binary analysis. And this technique help demonstrate better performance than traditional techniques. For example, recent research shows that deep neural networks beat human analysts in identifying binary function stars. However, the extraordinary performance of deep learning technique heavily relies on the success to accurate and sufficient labeled training data, and this requirement can be easily broken in security applications. Take malware analysis as an example. As we know that labeling malware is a time and effort-consuming process and requires specific domain expert. It is quite common that a malware analysis company does not have enough expert or cannot put enough effort on the current labeling process. This will result in large volume of unlabeled data and classes. And as time goes on, a malware family could evolve into thousands of subfamilies. If a labeler only have knowledge of the parent family, they will label all the subfamily into an union parent family and result in coarse-grained labels. To tackle the above low-quality label issue and enable high-accurate attack categorization, we develop a novel technique, FAIR. In the following, I will introduce our technique and demonstrate how to use it in real-world security application. First, I will give the problem scope and definition. As mentioned earlier, low-quality label mainly have two forms. The first are missing classes. That is, the label data cannot cover all the true classes. Again, in malware classification, it is unrealistic to assume the analyst have the knowledge of all malware families. To avoid labeling errors, he or she will conservatively leave the unseen family as unlabeled data. The second form are coarse-grained labels, where the labeler mistakenly group several classes into one union class. In addition to low-quality labels, it's also hard for a labeler to label all the samples. As such, another common practice is to have only a small proportion of labeled data in each known class. Last but not least, in this work, we do not consider noisy or corrupted labels. In other words, we do not assume the known class contains label error. Now I will formally define the problem of FAIR. Given a dataset with n true classes, we consider two setups. The first setup is missing class. In this setup, we leave NC classes as unlabeled classes and preserve only 1% of labeled samples in the other known classes. This figure here demonstrates an example of missing classes setup. The second setup is coarse-grained label. In this setup, we give original NG classes one union label and also keep only 1% of labeled sample in the other classes. The figure on the right-hand side here demonstrates a training set with one union class. Our goal in this work is to correctly identify that there are n clusters and correctly assign all the sample to these n clusters. Now I will introduce our proposed technique. At a high level, our system has three steps. In the first step, to extract useful information from the given data, we will apply multiple clustering algorithm on the training set. The insight of applying multiple clustering methods is that different clustering methods may have different assumptions on the data underlying distributions. And applying multiple clustering methods could adapt our method to different type of data distribution. Then to fuse the knowledge in the given label and those learned by the unsupervised clustering method, we then ensemble unsupervised clustering result with the given labels. With the ensemble result by hand, we apply contrastive learning to learn an input transformation function. This function will transform the high-dimensional data into a lower latent space. Thanks to contrastive learning, this latent space will have some nice properties. As shown in the figure here, the sample in the latent space are more separable in that the similar sample will have shorter distance, and the dissimilar sample will have a longer distance. Besides, unlike the original space, where distance between samples are oftentimes ill-defined, the distance at this latent space is well-defined and can be captured by the Euclidean distance. Finally, we conduct the k-means clustering to the latent space representation and obtain the final clustering result. Here are our technical details. Given a dataset with missing class, and coarse-grained labels, we first run 3 clustering methods on the given training set. They are k-means, dbScan, and a deep learning-based method, DEC. Table A here shows the clustering result of each method and the given label. Based on the clustering result, we then derive pairwise relationship of each pair of samples between each pair of samples and show them in table B. In this table, we can see that samples from the same class or same cluster are given the label 1, and samples from different clusters or classes are given label 0. After obtaining the pairwise relationship, in the second step, we then use the data, this pairwise relationship, and the weight of each model to learn an input transformation net through contrastive learning. The objective function of contrastive learning is here. This objective function will minimize the latent space distance between a pair of samples with label 1 and maximize the distance of a pair of samples with label 0. Finally, we apply the k-means cluster to the latent space representation and obtain the clustering result. Now I will presenting how to evaluate our system. We evaluate FAIR on 2 datasets, the Android malware dataset and the network intrusion dataset. We randomly split the datasets into training, validation, and testing set, and simulate different kind of low-quality label setting through the dataset construction method we introduced above. We then apply FAIR on the training set with these low-quality label settings to recover the underlying cluster structure and evaluate the learned structure on the testing set. We select the 2 evaluation metrics, the widely used unsupervised learning metric AMI and accuracy. We evaluate our system in 3 types of setups. There are no label settings, missing class settings, and coarse-grained label settings. Here are the results in no label settings. As we can first observe from this table, FAIR is more effective than the existing clustering method and ensemble clustering method. As we can also observe from the runtime column, FAIR's computational cost depends on the base clustering method, and it is significantly less computationally intensive than the ensemble approaches. Here are the results in the missing class settings. In this settings, we select three baselines, mix match and ladders. They are two widely used semi-supervised learning methods. This DN plus represents the baseline that directly applying a supervised DN classifier to the given training set. The table here shows the number of clusters recovered by each dataset, and the figure here shows the final AMI. As we can observe from this result, first, the supervised DN perform extremely poor when there are missing classes in the given training set. As we can also observe that FAIR is more effective than baseline in recovering correct classes and assigning sample correctly. Here are the results in coarse-grained label settings. Similar to the slides above, table here shows the number of clusters recovered by each method, and the figures shows the final AMI. The conclusions are basically similar with those in the missing class setups. Going beyond evaluating our system on standard dataset, we also apply it to a real-world application. Specifically, we apply our system to identify fraudulent accounts for an e-commercial service company. We collect the dataset with 20,000 active user accounts. Each of the user accounts is processed into a feature vector. The feature here are basically product information, shipping information, and purchasing information. Among this data, the security analysts from the company labeled 0.5% of fraudulent accounts and 0.1% of trustworthy users. We then apply our system to identify the untrustworthy user in this dataset, and we design an A/B test to verify the fair result. We prepare two groups of users. The first group of users are the fraudulent accounts identified by our system. The second group are accounts that been given a trustworthy label by the security analyst from the company. For both groups of users, we revoke their sign-in cookie and force them to re-enter their password and perform a two-factor authentication. We record their login attempt rate and the authentication pass rate. The results are shown in this table. As we can see from this table, none of the fraudulent accounts identified by FAIR pass the authentication. The security analyst from the company also conduct some manual analysis on the identified fraudulent cluster by our system, and they indeed recover some unseen behaviors, such as the dual hunter and the click farm demonstrated here. Overall, the results shows that FAIR could correctly identify fraudulent accounts and help discover new knowledge. To conclude this talk, first we show that low-quality label poses a crucial challenge to deploy supervised deep neural networks in security application. We design a technique shows that contrastive learning with ensemble clustering enables fine-grained attack categorization. Finally, we demonstrate that our system FAIR can serve as an effective tool for attack categorization in real-world security application. Thank you all for the attention. Our code and data are publicly available and can be found in this GitHub link. Now I'm glad to take questions.